Okay, good morning, everyone, and welcome back. All right, here we are in the course on environmental bioethics in the program of bioethics at St. Thomas University. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen. All right, so any questions or comments from previous lectures? We've covered the geophysics, we've covered the geosphere, then the atmosphere, and we see some relevant events. Even as we're talking now, there was a hurricane in the North Atlantic last week, and there's another one coming this week from the Caribbean. So many hurricanes form on the coast of Africa, on the west coast of Africa, and they travel precisely according to the pattern of currents from Africa or Europe to North America and the northern continent. Those winds, by the way, were called trade winds. Anyone know why they're called trade winds? You have to go back 400 or 500 years ago when trading was done by sail. So there were galleons, there were big ships, and the steam engine had not been invented yet, right? And so they followed the wind patterns. And that's why generally, so the Coriolis effect, combination of convection currents and Coriolis effect in the North Atlantic between the tropic and the 30-degree latitude, right? That's a general pattern of the winds coming from the east to the west. So it favored ships coming from Europe to trade in North America. And so that's why they're called trade winds. Each one of those currents has a name, the easterlies, the westerlies, and so forth. So that was last week. And again, keep in mind, it's a combination of the two types of currents. One is basically vertical, the convection current, which convection occurs in the geosphere. In other words, occurs in the mantle. It's thick, but it's molten, it's lava, right? So any fluid will be affected by convection for heat transfer. So heat rises and the fluid rises toward the bottom of the crust, right? And there it releases some heat that goes through the crust out into the atmosphere and eventually into space. That's the heat radiation of the Earth. And as it cools there or becomes less hot, then it sinks. And as it comes closer to contact with the core, with the outer core, then it heats up and does that same rotating motion. Generally, convection currents are vertical currents, right? You can think of a belt, a vertical belt. So that occurs in the geosphere. It occurs in the atmosphere with the, like the opposite end of fluidity. You can think probably one of the thickest fluids is lava, magma, right? Molten rock. And one of the thinnest fluids is going to be gas, the atmosphere, the air that surrounds us. But that is also, because it's a fluid, is subject to convection currents. And then, but that's not sufficient. It's necessary for the atmospheric weather patterns that we have, but it's not sufficient. The other current, if you will, the other motion is going to be what is known as Coriolis effect, which is kind of a horizontal motion because it has to do with the rotation of the Earth. It's spinning at the top, right? The Earth is spinning on its own axis, and that causes a rotating motion on the atmosphere. And so it's a combination of those two that has the weather pattern. That's why the weather patterns are fairly complicated, right? And there's always margin. There's fluidity precisely in the weather pattern. But it also occurs in the hydrosphere, which is what we're going to be talking about today, especially in the oceans and some lakes also. but mostly the oceans because they're large bodies of water and they are affected both by convection and Coriolis. So we have a similar effect. And there's a feedback mechanism that occurs between the atmosphere and the hydrosphere, meaning the oceans, precisely to influence weather, all right? Weather patterns, long-term weather patterns, especially seasonal. And we'll be looking at some of that today. So basically looking into the hydrosphere, which is the liquid component, the fluid as liquid, which will take up basically the bottom of the container, right? Which will be the beds of rivers, oceans, lakes, etc. All right, so we're going to look first at beginning with the smallest unit possible that is stable for water, which is water itself, the water molecule. And we'll look at some of the physical and chemical properties of water, and then the consequences of that as we magnify up to the natural state of rivers, oceans, ice caps, etc. And then we'll look at currents, oceanic currents, especially as, like I say, they influence the weather, and then the weather also has a feedback influence on the oceans themselves. We'll look at ice caps and glacier dynamics, meaning glacier and interglacial periods, because keep in mind, one of the issues here on the bioethical side is climate change and global warming, right? So we have to address that, but first we need to begin with the science, in other words, the data, and we'll do the ethical analysis always based on data, and that's why our ethics, Catholic ethics, is always evidence-based, because we look at what nature tells us, and based on the facts, then we do our analysis, okay, our ethical analysis. So we have to look at these glacial and interglacial periods, and then finally, more on the ethical side, the natural right to water, not just water, but drinking water, because if water is contaminated, then it's even worse, right? Because it makes me sick instead of well. So these are challenging issues, and I can tell you to the bottom line here is that water throughout the world is becoming more and more of a commodity that it's basically called liquid gold, all right, liquid gold, because it's becoming more and more scarce as the population increases, human population, and therefore we need to get more and more creative on how to have sources of fresh water available for people throughout the world. Because here, definitely in this bubble that we call the United States, we are very, very privileged. I mean, you open the tap water and you get drinking water, right? Okay. So again, if you have any questions or comments, jump right in, either from previous stuff, and try to be linking in some concepts from previous lectures, okay? One that is relevant and kind of in the background here is precisely the whole issue of liquid water. We take it for granted, but the fact that we actually have liquid water here on the crust of the earth, on the surface of the earth, is spectacular because it allows for that possibility of life, organic life as we know it. And we know that part of that has to do with the temperature of the earth as it's cooling and so forth, which means that there was a time the earth, we go back a few billion years ago, where life was not possible because the surface was just too hot and there was no liquid water, it would evaporate. Likewise, when we run the clock forward, there will come a time, because heat radiates out always, right? And there's an overall increase in entropy. That's another concept. Entropy is in principle a physical property, but it's important to understand existentially what that means. Entropy is essentially like heat energy that dissipates into the universe and therefore is unavailable for doing work. It's lost energy, lost. It's unavailable for doing work because it just dissipates, okay? And so there is a gradual but definite increase in entropy as the clock ticks forward. As we move forward in decades and eons and millions and billions of years, there's a gradual but sure increase of entropy throughout the universe. What does that mean? That the universe as a whole is gradually cooling In other words, the hot masses on Earth, in the universe, which will be either stars or planets or things like that, gradually cooling, losing heat. So if we apply that to our Earth in a few or several million years, we don't know how many, and the Earth will be so cold that we'll be unable to hold liquid water any longer, all right, at least at the surface. And we're finding that in other planets, that there may be liquid water underneath their crust, but not at the surface. At the surface, the water is frozen, like in Mars and Venus, but there may be some evidence that there's liquid water underneath the crust at some point, what would be underground lakes. And then the big question is there life in there? Or can we recognize it as life if we see it? Okay, exciting stuff. All right, so let's go back to the humble molecule of water.
Sorry, Father, how are you?
Yep.
Yeah, I have a question because it's interesting that on the thermosphere, that the temperature is so high, and there is the place where is the International Space Station is orbiting. So how come being so close to the, not so close, but closer to the sun, and the high temperatures are super high in that layer, how come the heat is not harming all this stuff? For example, the international space and also the radiation goes to the astronauts.
Yes. Okay, very good. So Dr. Farid is asking about the ISS, International Space Station, which is the largest artifact that we have created to date, right? This guy, and it is in the thermosphere there, orbiting around the Earth. And you can see these are actual photographs taken with the Earth on top, the Earth behind, right? Which, by the way, these are solar panels, right? For electricity, for running the station. It is international. It's a collaboration between the US, at least the ones that I know, the US, the UK, maybe France, Australia, Japan, Ukraine, and Russia. And I heard that recently the Russian astronauts are out of there because of the political situation that's happening. So how come this thing doesn't just melt, right? Okay, you said two things that one is very relevant, but the other one, be careful, because you said it's out there, so it's a little closer to the sun, not necessarily, okay? Not necessarily closer to the sun. First of all, it makes a difference. Let me see where I can go. I just want to grab from last week's lecture one diagram that will make it very graphic. Let me see here. Just give me a minute. Maybe this one. No, before. Okay. I'm looking for this guy. Yes, so first of all, they're closer to the sun, theoretically or hypothetically, yes, in principle, but only when the ISS is on the sun side of Earth, right? Because the ISS is orbiting around the Earth here. So when the ISS is on the far side of the sun, on the dark side of Earth, then it's actually further away to the sun than even the Earth, right? Okay, so it's just a technicality. For 12 hours, it will be closer to the sun, and for 12 hours, it will be further away from the sun. But even that is absolutely, totally irrelevant. Why? Because the distance from the Earth to the sun is not this distance that is shown here in this PowerPoint, but rather 10,000 times the diameter of the Earth. So I told you last week in one of the many things that I said in passing, just to put this diagram to scale. If the sun were to be this size, as you see it here, all right, the sun were to be this size, and the Earth would be this size, which I took the trouble to make the sun 100 times bigger than the Earth, right? So if we were to take this little blue circle and move it over, I should be able to fit 50 of these Earths over here in the radius, right? And another 50 on the other side to make the diameter. If it were to scale, this little blue dot of the Earth would be near the entrance or beyond the entrance of the university, which is about 5 blocks away, because we're near 32nd Avenue and the entrance is on 37th Avenue. So 5 blocks away, this little blue dot. We wouldn't even be able to see it from here. Okay, that would be to scale the 10,000 times. So you can see that the distance when, let's say that when the ISS is on the sun side of Earth, right, during daylight, that distance, little closer to the sun, yes, technically it is, but existentially, it makes no difference. You know, it makes no difference. It's like the difference of the thickness of a hair, of a human hair, in comparison to from here to New York or something like that. You know, it makes no difference, right? If we're a hair closer to New York than where we actually are right now. All right, so that makes no difference. What does make a difference is the radiation. By the way, the heat doesn't make any difference either, because heat dissipates, right? Light does dissipate also, but there is radiation, especially the UV and all that. That does have an impact on the ISS. Therefore, what's very important about the ISS, that is totally shielded. And you know, they've gotten very creative with doing alloys. An alloy is a mixture between metals, for example, or 2 or more compounds to make a new type of material that has, for example, can be, you know, 50 times stronger than steel and maybe 100 times lighter than steel. These are alloys, all right? And it's called materials. What is that? Materials engineering or something like that? Okay, it's one branch of engineering that is constantly researching how to make materials to specific qualities. In the case of stuff that is going out into space for building stations and all that, you know that right now we are engaged very much in a project of stabilizing, of generating a colony in the moon, a human colony on the moon, right? You heard about the, what is the name of the Artemis or Arenas or something like that? What is the name of the project? Anybody offhand?
The rocket is Artemis,
Artemis,
but I don't know that. Yeah, I don't know the project itself, but I think so.
I think it's the Artemis project, or at least a rocket. Yeah, it was supposed to take off last month sometime, and there was they detected some kind of a leak, a fuel leak, and so they stopped everything. And I think they have now that fixed, and so this Artemis rocket is to be taking off soon. This one is unmanned. I think it's unmanned, yeah, but they're doing, it's going to land on the moon, it's going to put a rover there, and so on and so forth. And it's the beginning of a project to eventually have a human colony on the moon. Of course, it will be very few people, you know, we're not going to build a Manhattan up there or anything like that. But the materials that have to be taken there, right? Part of those materials would be machinery to make machines. Interesting. So if we get a factory going on the moon and use moon rock, so the moon soil is very similar to the Earth, has similar composition. So whatever we find here, generally we find over there, you know, including metals and so forth. So to establish a factory on the moon to make things and to print them with the 3D printers and stuff like that, to make tools and all that, and to make more machinery like panels, etc. Well, alloys will be very important, right? First, they have to be light once we send them over there. But once we get that factory going, then they don't have to be light anymore because they're being mined on the moon and being manufactured on the moon. So instead of, we may have some stuff made in the moon instead of made in China at some point. It's not gonna be that cheap though. But anyway, the ISS, so shielding basically protection, and that's why the spacesuits also are are very expensive. They're custom made, tailored to the individual astronaut. Okay, but in thin layers, they can cause a lot of shielding. But you know, the human body is not that far away from a very, very sophisticated type of shielding. When you consider, for example, what's the room with the temperature here right now? The temperature in the room, for those of us who are here, it's nice and comfortable, right? It's certainly air conditioned because it's warmer and more humid outside through the walls here. And so I would say it's in the 70s probably here, 70s. What do you think it's outside the wall? At least 80s, right? And give it a little more time, it may get to the 90s. So consider the block, the cinder block, the concrete block that is made of this wall plus the plaster over here, and they're stuck on the other side. So there's quite a bit of insulation between the room and the outside temperature, just for 10 degrees, right? But consider this, what's our internal core temperature? 98.6, 0.7, whatever, 98, almost 99, almost 100, not centigrades, right? Because if it were centigrade, we'd be boiling. It's Fahrenheit. But 98, let's run it up to 100, just slight fever. To 70, that's almost 30 degrees Fahrenheit of difference. And we don't have, so the internal core, how deep is it from our skin through our chest or through our abdomen, from our skin to the heart is maybe an inch or so. Medical doctors, what's the distance from the skin to the heart, approximately? An inch, 2?
I'll say like 2 inches.
Even
Yeah, it's about, it's about 4 centimeters, 4.5 centimeters.
4 inches?
Yeah.
Wow, that's a
No,
lot.
centimeters.
Centimeters.
Oh, 4
centimeters.
centimeters. Yeah, 4
Yeah,
centimeters.
I don't know inches in human.
Well, 2.5 centimeters per inch. So it's less than 2 inches. Yeah, it's 2.5, about 2.56, I think it is, centimeters per inch. All right, so about 2.5 centimeters, a little.
Yeah,
over
I
double.
was just thinking of the needles we use to pierce the heart.
Yeah,
Called the
there you go.
pericarditis.
Leave it to the cardiologist.
No, I actually I worked in the cadaver lab over the summer and we were able to actually go into the body.
Mhm.
So yeah.
Yeah. Exactly. So consider, the core is very near the surface by the inch. And yet that distance between skin, adipose tissue, which is fat, and muscle, and some tendons and ligaments there, conjunctive tissue, it's extremely efficient insulation because it's maintaining the core, 20 to 30 degrees difference in Fahrenheit. That's more than this wall is doing with a much thicker insulation. So the human body and bodies in general, because they have withstood evolution, including the radiation that has filtered through the atmosphere to hit the earth, right? Anyway, so it's a long-winded answer to your question, doctor, but it's all about the insulation because space is extremely inhospitable, all right? It's either extremely hot or extremely cold and vacuum. So basically everything blows up there. If it's not well insulated, if it's not well held together, well welded. Okay.
Thank you, Father.
Okay. You're welcome. Thanks for the question, but we're thinking in those terms. All right. It's good to think out of the box, as it were, into space. This is a time also to think about space. All right, so let's look at the humble molecule of water, because I can tell you water is very unique in its properties. It's kind of not behaving like it's supposed to, or rather, well, it is behaving like it's supposed to, but it defies the normal properties of atoms and molecules for the actual molecule of water itself, okay? It's very unique in nature. So the first thing you notice, of course, it's got 1 oxygen and 2 hydrogens, right? So the oxygen is, but the charges, so hydrogens are positive, basically the protons with the electron orbiting around the the oxygen atom, okay, that's called a hydrogen bond. Now, but you notice that the hydrogens are displaced from the equator. They're not at the equator, all right? That's because of the particular properties that there is extra negativity on the oxygen, so it pushes the hydrogens off center or off the equator, as it were. The net result of that with charges is that water has a negative pole and two positive poles on the opposite end of the molecule, all right? So it's like a magnet. It has a positive end or two little positive ends with hydrogens and a negative end on the other side with the remainder of the atom of the oxygen atom, which is obviously larger than hydrogen, right? So think of a magnet, but at the molecular level, super tiny microscopic. Well, then when you have two or more water molecules together, they're going to start interacting because the negative pole of one molecule is going to be attracted to one of the positive poles of the other molecule, but not both, one to one, because that's the ratio, all right? So one of the hydrogens is going to be attracted to the negative pole, totally opposite from the other two. And it's a double thing because not only is, let's call this the North Pole, the negative, and let's call the South Pole the positive, right? So the North Pole is going to attract one of the hydrogens. But in addition to that, there's also a repulsion. Positive to positive repulse each other, right? So there's also a slight repulsion of this molecule 2 hydrogen from the molecule 1 hydrogens. Okay, so on 2 counts, this hydrogen from the second molecule wants to go over here as far away as the 2 other hydrogens, but close enough to interact with this negative charge. All right, so it's a very, very interesting dynamic that is occurring. And that's just 2 molecules. Now add on one more molecule. One more molecule could go, now it's got 3 possibilities, right? The negative could go to hydrogen 1 on molecule 1, or hydrogen 2 on molecule 1, or hydrogen 2 on molecule 2, because hydrogen 1 is already taken up with molecule 1, you see. But there, when 2 water molecules come together, 3 positive poles are available, but 1 negative pole is still available, which is on molecule 2 here, all right? And that's just 2 molecules interacting. Now throw in a gazillion molecules will be in a single drop of water, and imagine the interaction that is occurring. The fluid interaction that is occurring between these molecules is super, super dynamic. So basically, they are slipping around each other. They're slipping around each other in the liquid state, in particular, okay? I'll have a little more to say about that when we see another diagram further down. But so one of the properties of water then is that it tends to coat other molecules and other matter, all right? Other matter, whenever the other matter is either positive or negative, it will be coated by water, all right? And so that's what we call hydrated. So other molecules or matter, mass in general, will be coated by water. That's why when we wet a paper, the paper will stay wet for some time because of the magnetic thing, all right? And and also that makes water what we call the universal solvent. Most substances dilute in water or go into solution in water, all right? So we call water the almost universal solvent. What doesn't go into water? The fats, greases, oils, and waxes, right? The lipids of the organic molecules, the lipids don't dissolve because they're neutral, right? So they don't feel attracted to water. However, those lipids, fats, oils, greases, waxes, they dissolve in alcohol, and alcohol dissolves in water. If ever you want to dissolve an oil in water, dissolve it in alcohol, and then that solution you can dissolve in water. All right, so it's a roundabout way. Anyway, this property of water being the almost universal solvent that most substances, certainly in nature, dissolve in water, is a very unique characteristic. And it allows it to be also then the solute for metabolism, the chemical reactions that occur in water. It's a benevolent environment in which to be, is immersed in water. All right. Okay. So let's, at the same time, it's a very stable molecule. So whereas it lends itself to coat other molecules, it itself does not dissociate. It stays stuck together because of that, precisely that hydrogen bond of the electron orbiting around the oxygen. Okay. All right. Let's look at the three states, still looking at the physical and chemical properties of water, the three natural states, gas, liquid, and solid. Of course, we know that by the gas laws, we can change those states by adding or subtracting temperature, right? By adding or subtracting heat. And we know that the limits are for freezing water, it's going to be 0 centigrade or Celsius, and which is equivalent to 32 Fahrenheit. And for boiling the water, it's going to be 100, which is equivalent to 212 in Fahrenheit. So almost double the number, okay? Now, this scale, so you see that the centigrade scale goes from 0 to 100 on purpose. This is what we call a convention. It was established this way. It's not a convection, it's a convention. In other words, by agreement, by international agreement among scientists mostly, it was established a long time ago that we will use water, the two changes of state of water, to develop a temperature scale that is a decimal scale. In other words, it's in units of tens, right? And essentially 10 units of 10 fit in 100. And so that's just by convention, it was established that way. And so to this day, that's because it fits into the metric system, that's the scale that is used, centigrade. And this goes back to the Greeks several centuries before the time of Christ. And that's why it's also called Celsius, because this was the Greek guy who invented this convention back several centuries before Christ. And his name was Celsius. Okay, so whenever you get to invent something, you'll put your name on it. Now, notice here, we're gonna pick it up in a moment, but notice here that in the three states of water, the solid state is actually a crystalline state. It's a crystal water, all right? That's ice. The liquid is normally what we talk about. When we talk about water, we normally refer to liquid water. And then gas, the molecules are dissociated because there's enough heat provided to the to water for the molecules to dissociate. And now the water gas, which is known as water vapor, the molecules are dissociated from each other, so they're moving in random motion. They're not slipping and sliding around each other, they're bouncing off of each other because there's enough heat that was provided, typically 100 degrees or more, to dissociate the molecules. So it's a random motion in the gas. And that's also why it burns, because it's very hot. Let's look at specific heat then, because each molecule, each matter is mass, each material has what we call specific heat, all right? And the units of heat is in joules. That's just, this is the other guy who get his name, Dr. Joules, to put his name on the units of heat, all right? Again, it's a convention, and it's a little over 4 joules of heat to increase 1 gram of water by 1 degree Celsius. That's, again, the convention, right? That's known as the specific heat. How much does it take, how much heat does it take to raise 1 gram of this material by 1 degree Celsius? Whatever joules it takes, that is the specific heat of that material. all right, of any material. It could be a metal, it could be a crystal, any element of the periodic table, any molecule, whether it's organic or inorganic. And for water, it takes a little over 4 joules to increase 1 gram of water, which is a very tiny amount, by 1 degree Celsius. All right. Now, to put it in contrast, for example, copper, we're all familiar with copper, right? Copper wiring and so forth, it's a metal. And to increase copper, 1 gram of copper by 1 degree Celsius, it takes less than 1 joule. It takes less than half a joule, 0.385, okay? So you see the contrast. It takes 8 times more than 8 times the amount of heat to increase 1 gram of water than 1 gram of copper to 1 degree centigrade. And that's why copper is also a good conductor. It transmits the heat right away. And that's why it's used at the bottom of pans, good pans. That's why they're expensive, because copper is expensive, becoming more and more expensive. It's a good conductor. It's used a lot in electricity and so forth. And it transmits the heat very quickly, whereas water retains heat. Does not transmit it as easily. Water retains heat. So that has consequences, many consequences in the environment, but 2 big ones are, for example, that by retaining heat, then winters are milder and summers are cooler with in bodies of water. All right. And that's why, for example, at night, when you go into the pool can be warmer than in the atmosphere, than the air around the pool, simply because the air holds less heat. There is some water vapor there, okay, but the air holds less heat than the liquid water of the pool. And that also has influence local weather conditions for cities or towns that are near the water, whether it's a lake or an ocean, because there is more heat there and it will retain more heat. To illustrate this pretty graphically, look at this graph here. Look at this, not graph, but image, all right, of heat on the Earth. So why does this Earth, first of all, why does this chart look, figure is flattened out like that? It's not a realistic, well, it is realistic. That's the point is that when we try to project a sphere, surface of a sphere, right, on a flat surface is very difficult because the sphere is 3-dimensional. At every consecutive point, the sphere is concave or no, convex. It's turning around, right? It's a curvature. So how to project a curvature on a flat surface, 2-dimensional, is always very challenging. That's why maps are challenging. So that's why it looks awkward a little bit like this. And typically, the one that takes the hit is Antarctica down here, which is a continent, in contrast to the North Pole. So a little bit more about that in a minute. But basically, this is a projection of the Earth, more accurate around the equator than at the poles, showing the continents, showing the major continents, North and South America, Africa, Eurasia, which, by the way, continentally is a single continent, Europe and Asia. It's a tectonic plate. Then the subcontinent of India down here and Australia. What is missing again is Antarctica down here, but it's mostly for the oceans. You know that 3/4 of the Earth's surface is ocean, okay? And so you can see the temperature is warmer around the equator, north and south of the equator, about 30 degrees, more or less, latitude, north and south, right? That's the hottest part of the Earth and the oceans. And then you have the temperate zone in the yellow transition, temperate zones. And then eventually the poles, the cold region. But you notice that the North Pole is less cold than the South Pole, right? See how this violet and white goes to the edge of the scale here, -40, -50, we don't get that effect up in the North Pole, not as drastic. It's cold, but not as drastic, except for Greenland, of course, which has a glacier on it, right? Purple to -30. And why is that? So the South Pole, Antarctica, is an actual continent, right? Whereas the North Pole is mostly water, even if there is a cap of ice up there, okay, the Arctic Circle, but it's mostly water. And so land gets colder than water. That's the whole point. That heat, there's a little bit more retention of heat up here. So it does get cold, but not as cold as the South Pole, because in the South Pole, there's an actual continent. And land gets cooler than water, because water retains more heat than land. All right, so this is, when you study this a little bit, you see how water retains heat, and it actually has an effect on the global weather and climate, affecting the North Pole and the South Pole differently. And this is in spite of the fact that the Southern Hemisphere generally has more water than the Northern Hemisphere at the surface. Anyway, why? Because most of the continents are in the Northern Hemisphere. It's another, I've mentioned this before, but some people think that the equator is somehow between North and South America, you know, around the Caribbean, and kind of high on Africa, but it's not, it's very low. This is the equator. This fictitious line here is representing the equator. And look at how low it is on the continents. You know, it's almost, well, it's definitely way into South America. It's almost at the thickest part of South America, which is Peru on the west coast and Brazil on the east coast, almost smack across the Amazon, right? But look at Africa. So anyway, still in North America, most of, I mean, Venezuela, Colombia, all that is above the equator. And certainly Central America and the Caribbean is way above the equator, even though it's warm. And Africa, look, it's in the southern part of Africa. It's the southern tip of Africa. Most of Africa is above the equator. And then it cuts right through the Singapore and the Polynesian Islands and Southeast Asia. This general area is called Southeast Asia. And Australia is in the southern hemisphere, but fairly close to the equator also. It's really okay. So most of the southern hemisphere surface is water, either Pacific, Atlantic, or Indian Oceans. Three oceans down there. Okay, back to the physical chemical properties of water, because it's going to make a difference when water freezes and thaws. It is a humongous erosion factor. Erosion factor. Consider this. Solid water, they're crystals, all right? They're crystals of water. These are snowflakes, and each snowflake here, it has a particular pattern, myriads of different patterns, but they're all geometric patterns. And they have a slightly different pattern simply because they have to start with a tiny microscopic grain of dust, you know, or some kind of impurity. That impurity, of course, think about it with your mind's eye, is never going to be the same. 2 grains of dust are never going to look the same, right? At the microscopic level. And so molecularly, those little patterns on the edges and so forth, that's where that serves as like a seed to begin the crystallization process, right? And so that's why snowflakes are a myriad different shapes, but they're all a geometric pattern. You can always cut them sideways and get a mirror image no matter where you cut, all right? All right, as long as you go through the center, through the dust particle. All right, so water, when water freezes, it's a crystalline structure, right? Meaning that it takes on this kind of shape, kind of hexagonal. You see, the hydrogen is connected to the oxygen, hydrogen to oxygen in a very geometric pattern. all right? Whereas liquid water with higher temperature above 0 centigrade and below 100, right? Liquid water has enough heat to break the crystalline structure. And when it breaks the crystalline structure, liquid water the molecules get closer to each other. Again, in a dynamic state, because in a crystalline structure, the molecules are kind of in place and they may be oscillating, they may be vibrating, but they're not moving around too much because it's a crystal. So they're kind of fixed, right? They may be oscillating within the molecule and the atoms, but they're kind of fixed in a crystalline structure. But in liquid water, again, because of the heat that has been provided, now the molecules are slipping and sliding around each other, and they can do that in a tighter conformation. The end result of this is that when water freezes, it expands, which is a very unique property of water. When water freezes, it actually expands. It's counterintuitive, right? Because with decreasing temperature, what should happen to the molecules? They condense. And in fact, that does happen when we cool down water vapor. When we cool down water vapor, it condenses into liquid. It does condense because those gas molecules are now clustering together. But they cluster together so tightly that they form a very, very compact formation. But then when we continue to take out temperature from water and now freezes, it expands slightly instead of compacting even further because it cannot compact any further, which is another property of water in the liquid form, that liquid water is essentially incompressible. Incompressible. Think about that. Drastic. When I was a teenager, we lived in Mexico City in the 60s. That was the 1960s, okay, not the 1860s. And in Mexico at that time, there was a very tall tower, which was the Mexican equivalent of the Empire State Building, and it's called the Torre Latinoamericana, right, in Mexico City. There it is to this day, it's still around. Of course, at the very top, it has a radio station and whatnot. Torre Latinoamericana, it's a huge building in Mexico City. I mean, Mexico fluctuates, population is one of those megalopolies that has more than 10 million people. It fluctuates between 25 and 40 million people, huge among us. Yes, a lot of smog there also, precisely because of corruption, essentially, of the lack of control of emissions, carbon emission, transportation, industry. But anyway, Torre Latinoamericana, you know, it was a huge building back then in the 60s. None of these other towers were around, buildings. And Mexico is also, Mexico City and the whole valley there, the whole valley, it's a seismic area because it's near the mountains and it's seismic. And so there are tremors periodically. And the feat of making this tower back 60, 70 years ago is that the foundations are floating inside water pools of water. So this whole humongous building is floating inside a pool of liquid water, okay? And that liquid water is so incompressible that it holds the building afloat, but it also absorbs the shock. So if there's a tremor in Mexico City, what happens is that vibration goes into the water pool, which is a humongous water pool, and then the vibration dissipates through the water, okay? And it's not transmitted to the building so that the building doesn't collapse. And it's been there for 70, 80 years, I don't know how long. And there have been many, many tremors. In fact, when we were there, we had more than one tremor. I literally saw buildings go like this in front of us. It's a very shocking thing. You know, those were minor tremors. But The tower is still there, and many other buildings are falling in those 60, 70 years, because it's inside an enormous pool of liquid water, because liquid water is essentially incompressible. And the reason for that is because these water molecules individually are so tightly slipping and sliding around each other that there's no room for compressing them even further. Okay, so very interesting properties of water that has a lot of impact on nature. First, to allow metabolism to occur, and beyond that, for erosion. So let's look at erosion here when we consider, especially in the temperate regions where you have the 4 seasons more or less evenly, and the winter there will be freezing, in the summer there will be thawing, of course. So what happens? Water gets into the cracks of stones, boulders, and even entire mountains, right? Water gets in there. And by capillarity stock, oh, that's another characteristic of water that I didn't have here. By capillarity, water can actually go up a surface because of that creeping of the water molecules attaching. It's what looks like a glue. It's not glue. It's actually a magnet. It's a positive, negative attraction that is occurring. Anyway, water in the summertime, let's say this boulder gets water inside these cracks, right? And then in the wintertime, that water freezes. When it freezes, what is going to happen? It's going to expand. And when it expands, it cracks the rock open. And you can see it here very graphically. It's an actual photograph of a boulder that was cracked, right? By water seeping in there and freezing and expanding and cracking the rock. When you add this year after year, century after century, millennia after millennia, it causes tremendous erosion, bringing down entire boulders, boulder fields and stuff around mountains that erodes, okay? And this can happen from the largest rocks to the smallest ones. At the same time, there's another type of erosion that happens when rivers run through a valley. For example, the Grand Canyon. The Grand Canyon, this was a valley up here, flat. It's part of the Great Plains, right? Right, so you see horizon is flat. There are no mountains here. Actually, what we have, the Grand Canyon, is crevices. So the top is flat, right? And the water dug a hole, carved through the ground, mostly sedimentary rock, carved through it and took all that sand, silt, and soil out to the Gulf of Mexico. And deposited there. And that's also why the Gulf of Mexico is more shallow, because the sediment has been rising and rising and rising. The dumping of materials of sand, soil, and silt from the Midwest, the Great Plains, down into the oceans. Okay, so rivers generally end up in oceans, carrying all the stuff with them. So that's a different type of erosion that happens with liquid water, right? Over eons. It also happens at the delta of rivers. For example, you see the dynamic state of this delta as this river empties out into an ocean. And it also happens with ice, with glaciers, because a glacier is a river of ice that moves slightly but continuously, all right, through the mountain range. And typically the glacier is fed by what ice? At the beginning of the glacier, I think it's called a cirque. The beginning of the glacier is fed by what? By snow. Year after year after year, the snow keeps accumulating. And after a while, snow is heavy because snow is water. That's why the rooftops and buildings up north, especially houses, are steep, right? The steep gable, so that the snow will run off, because snow is water, and when it accumulates, it's heavy and can break through. So the snow accumulates at the beginning of the glacier, and that snow, as it accumulates, we're talking feet and feet and feet of snow, it starts pushing down and out. So the glacier starts moving down slowly but surely, all right? And as it moves down very slowly, maybe just a few inches a year, but it's moving down, all that water is heavy, all that ice, and it's grinding the stuff underneath. So that's why at the bed of glaciers, nothing lives there, maybe some frozen bacteria, okay? And it's grinding the bottom, and that also has a huge erosion effect on mountain ranges, okay? Until eventually at the mouth of the glacier, well, that glacier will be melting into liquid water, and typically those are the beginnings of rivers, riverlets and streams that will eventually become other rivers and do this kind of erosion. There's a certain cycle also that occurs with rivers in particular that is very interesting, because a young river goes kind of straight. The water is following the path of least resistance, right? There's a slight inclination, the slightest inclination on that topography, while water is finding the path of least resistance by gravity being pulled down, right? And so as it runs, it's going to start carrying material with it, again, sand, silt, soil, and as that sand, silt, and soil and pebbles move with the river, they are causing more and more erosion. So eventually the river starts meandering left and right, because again, is seeking that path of, or following the path of least resistance, where the pebbles are a little more loose, and this can even be down to the microscopic level or to the miniature level. You know, the silt is softer and so forth. That's where the river will go. And it would generate a general pattern of this S shape, back and forth meandering. With time, what happens is, again, because of the fluid dynamics, think in your mind, the water on this edge, on the outer edge, is actually running faster, right? Because it has to cover more distance in the same amount of time, which means that it will go faster on the outer edge of the curve, which means that there will be more erosion on the outer edge of the curve. So once a curvature establishes, that curvature will continue to impinge more and more outwardly, either to the left or to the right of the river, because that's where there's more current. The water has to cover a greater distance in the same amount of time, which means that it has to go faster, right? And so it's causing more erosion on the outer, which means that it's increasing the curvature more and more and more laterally, all right? So old rivers are very S-shaped. And not only that, on the inner side, precisely because the current is slower, there's more deposition. So more sediment, silt, and soil gets deposited on the inside of the curve, again, pushing the river outward. So it's a double dynamic, right? And sometimes, eventually, the river gets so old that these necks pinch and cross and eventually break through, and the river starts becoming more straight again. When the curvatures start pinching and the necks break through, right? It causes a more even path again with faster water coming through. And so after it has done like one layer of sediment and taking it out to sea or to a lake, it will begin again a second layer of digging in naturally. And it will continue that as long as there is water flowing through the river will continue to eat into the soil or the terrain that is around it. Interesting dynamics. So it is a dynamic system, all because of the running of water above the surface, right? And over generally long periods of time. Then sometimes we get another dimension of the dynamic, which is seasonal, especially in the temperate regions of the earth, right? Between 30 and 60 latitude, more or less, north and south, even though most of the land mass is in the north. Why? Because there's also the seasons. So you have a season in the wintertime, most of the water will be frozen, including rivers and lakes. There will be animals that hibernate even underneath that layer of ice, right? Like fish and some reptiles, and then some amphibians perhaps. And then when it thaws in the summer, there will be more rush, or rather springtime, in the thawing of spring, there will be more rush of a river. So when a river in the temperate region is more seasonal that way, it's an extra dynamic that adds more or less water flowing through that river seasonally, year after year, okay? So we have to keep in mind these dynamics are all caused by the flow of water. Let's go back to the molecular level for a moment. This another property of water is its surface tension. Again, these are properties that are fairly unique to the liquid as we know it, to liquid water. All liquids have a surface tension, okay? But some liquids have a very low surface tension, like the alcohols, for example, the phenols, anything that ends with OL, right? They evaporate easily. They evaporate, okay? So the surface tension is very low and it breaks off. In fact, the surface tension tends to, the capillarity, the meniscus tends to be going up instead of down. So water has a relatively high surface tension, relatively high. It's hard to see here, but let me see if I increase this. If you can see what I'm trying to show. Notice that the molecules on the surface of this water, right, are a little tighter together. They're closer together. They're as close together as they can be. For example, you see the distance between this hydrogen and this oxygen, right? It's a fairly small distance. The distances here are fairly small compared to the distances down here. It's a little bigger, right? That's because on the surface of the water, there's no more water on the top. There are no more water molecules associated with the liquid, right? This is the upper layer of molecules. So these molecules at the very tippy top of the surface only have the lower molecules to interact with, right? To interact. And therefore, they're attracted to they form like a seal, a shield, or a coat. So the end result of these dynamics is that the surface tension, the surface molecules are tighter together with the liquid fraction of the water underneath, right? And so they form a relatively high surface tension or resistance. Resistance to everything. Resistance, for example, to evaporation. There's always some interaction occurring at the surface of some molecules leaving spontaneously and some molecules, some gas, water gas molecules, water vapor molecules getting trapped into the liquid, all right? There's that dynamic interaction, but relatively little if the temperature is below 100 centigrade. So the water molecules is fairly stable and it evaporates relatively slowly because the surface tension is relatively high. So high that it allows some insects and other creatures to actually float on top of the water without breaking the surface tension. That's why you see this meniscus is a negative meniscus, right? It's bending in, but the legs of this creature, which is called a water strider, there are some spiders that can do the same, etc. Typically what they have at their legs microscopically is a lot of hairs or setae, they're called setae or hairs, and they increase the surface temperature tremendously, many times on the legs, on each individual leg of the insect. And so that it doesn't break the surface tension. You can do something similar with a little simple experiment. Oh, I haven't asked about the experiment from last week. Okay, a little simple experiment you can do later this week is just take a glass of water, fill it close to the surface, all right? Don't let it spill over, but get it close to the surface. And then you're gonna need a needle or a pin and a clip, right? And you wanna bend the clip to make like two little tongs. You want to bend the clip to make like two little tongs or to grab the needle, or you can grab another clip also. So you can use two clips. One clip you unbend and make like two little arms, all right? And then the other clip you just lay horizontally on those arms and lower that clip slowly on top of the water. And if the clip is nice and clean and the water is nice and clean, the clip will not break the surface tension, because that clip, the paper clip, is light enough, and it's even metal, it's not plastic, all right? So plastic naturally floats, but metal paper clip, if you lower it very slowly, it will not break the surface tension, right? And that's why, and that's the property of water. Now, you want to break the surface tension, you need to disrupt these molecules here. So you can add 1 drop of alcohol, for example, add 1 drop away from the clip on another side of the surface. And as that alcohol spreads through the surface of the water, it breaks the surface tension and the clip will sink. Once it sinks, it's now coated with water, so you cannot get it to refloat again. You have to use a dry clip. But so that's a little trick you can do to observe the surface tension. That's why water beads, it forms beads on top of things. You know, the meniscus is a negative meniscus, right? It's not bending the other way. Also, look at the surface tension on the face of this swimmer. You know, this swimmer's face doesn't look like this naturally, all right? That's a phenomenon of a lensing effect. You know, this swimmer is not a highly abnormal swimmer, doesn't have the pointed head like that or anything. It's just a lensing effect. But look at the surface tension. She has not broken the surface tension yet to breathe. She needs to do that any second now to get that breath of air, right, on her backstroke. But she hasn't broken the surface tension yet. Look how high it is. She's right under the surface of the water. So that's surface tension. Other characteristics that have an influence in nature. What else? Well, this is ocean erosion, which is one of the most drastic ones along the coastline. That pounding of the waves on the rocks makes a lot of the pebbles and the sands. Even though most of the sand actually is made, most of the sand on the earth, on the oceans, is made by a fish called a parrotfish. And this parrotfish, there are several species of parrotfish, but the common characteristic of them all is that they have a hard beak, right? They have this hard beak, and that hard beak allows them to chew on coral. They chew on coral, all right? And then they chew on coral, and after they chew on coral, of course, they swallow that whole because they don't have teeth to chew, but they eat on coral, and then they digest whatever living matter is on the coral, and then they poop the rest. And the poop, the excrement, comes out as sand. And so all these parrotfish eating coral over millennia and millennia all over the world have made basically the sand basin of the oceans, okay? So by pooping sand. However, some of that sand is crushed corals and crushed stones and rocks from the shoreline of ocean erosion. Now, the erosion is more drastic, of course, along sandy areas, as you can see here, right? It makes interesting formations as it carves through. These, by the way, are the I don't know if you've heard of the cliffs of Dover. Have you heard of the cliffs of Dover? Dover is in the UK, and it's across the Northern Sea with France, with Calais. Calais was very famous during the Second World War. It was D-Day. It was the landing site of the invasion, the Allied invasion of Europe to cut down the Nazis. And that was 1945, right? But basically, these are the cliffs of Dover. It's all sandy, very high. And it is said that you can see the cliffs of Dover from France. I was looking for a map. There's the map. Go back. Oh, sorry. Here. Oh. Okay. Let's see. All right, let's look at the map. These are actual photographs. It's just amazing. Here we go. It's over. They're opposite. So this is the British Channel or the English Channel, right? The North Sea, just for perspective. Here's the Atlantic Ocean, the North Atlantic, Ireland, the British Isles, continental Europe over here. Okay. And the English Channel, petroleum and all that. So this distance is about 20 kilometers, I think. And it is said that you can see the cliffs of Dover. They're so high and so big and massive and white from the French coast. All right. And yet, you know, when a human being stands on the horizon and looks out, how far out can we see, more or less, because of perspective, because the earth sinks below the horizon, right? An average height of about under 6 feet of height, 5'7", 5'8", we see about 5 kilometers out. And then beyond that is sunk, about 5 kilometers. So this is about 20 kilometers. And yet this coast can be seen because those cliffs are so massive and high, and it's all sand. Okay, erosion. And it's active, meaning that on this coast, no one builds near the coast because every now and then you have one of these come down, tumbling down. As you can see here, this inlets, it comes tumbling down, crashing to the ocean. Finally, I want to talk about the mangrove that we have locally and throughout the world, generally in the tropical regions, because mangrove stabilizes the coast. And mangrove prevents erosion. You can see it here even on this photograph with a little imagination. You see there's mangrove here. Mangrove have these aerial roots that go into the sand, right? And they stabilize the coast. So there's mangrove here, but then when there's no mangrove, the erosion of the ocean goes in and starts taking out sand and causing erosion. And so the ocean eats up into the land, like here, for example. Okay, you can see very graphically that this land used to continue out flat, you know, and it's all gone now. So the mangrove stabilizes the coastline, and that's why now finally it's protected, at least in the US and other parts of the world, still being cut down for urbanization, and also because it has a lot of tannin. Tannin is an acid, tannic acid, which is brownish, and is used for tanning hides, for curing hides, you know, like animal hides, like cattle, and to make the Gucci purses and all that stuff. Tannic acid is used for tanning, for curing the hide. And so in many parts of the world still, tragically, mangrove swamps are being cut down, mangrove groves for their tannic acid, which is a tragedy because then that ocean is going to erode into the land and land will be lost. Shoreline will be lost. Finally, now there's an ordinance in Dade and Broward County to protect entirely the whole southeast coast, I believe, to protect the mangrove.
Father Chofi,
Okay.
I have a question.
Yes. Mhm.
Thank you. So basically, the beautiful sand is what you explained, the poop of that fish. But why does it? Why there's so, like for instance, in Marco Island in the west coast, it is so white and almost crystal.
Yeah.
While in the east coast is more dark and less inviting. I just wonder.
Yeah, it's more powdery. It's a combination of factors. First, the geosphere, in other words, what is available, if it's more coral or if it's more other animals, like for example, starfish, or there are a lot of sand dollars in the West Coast. We're talking about the West Coast of Florida, okay? And I want to keep that map and I want to go here, sand dollar. A sand dollar is actually a, oops, sorry about the images. All right, a sand dollar is related to the sea urchin and is related to a starfish. It's kind of a combination between a sea urchin, flattened down, and the starfish that has pentagonal, has 5 legs, right? But it's a creature, it's a living creature, and it has little, small, little tiny spines around it. But the skeleton of the sand dollar is basically calcium carbonate, which is similar to the skeleton of coral. And so when the sand dollar breaks down, it has a lot of calcium carbonate mineral, which makes the beach white, sandy, almost crystalline, like you say, and powdery. So it's a lot of abundance of these in the West Coast because it's very flat and they bury under the sand. They bury under the sand. Okay, that's how they live. See, they pile up. Sometimes periodically you get this effect where the coastline is covered with these sand dollars because they're very abundant. Here you see them half buried and half out. Okay. Whereas on the East Coast, it's more shells, seashells, which are a little harder. And so it makes for more coarse sand. Now, also keep in mind that it's a combination. The parrotfish, they eat coral, but they don't eat conch and they don't eat shells because those are a little too hard for them. So conchs and shells, and also some of the coral skeleton is also broken up by erosion. So it's a combination of factors, okay? It's a combination. So part of it is just the erosion of the ocean currents and tides on the shore, and part of it is the parrotfish. But specifically in the Gulf of Mexico, there are a lot of these sand dollars that when they die and break down and just ground up into a fine powder like calcium carbonate, all right? Similar to bicarbonate. Bicarbonate, bicarbonato de calcio, which is in your medicine cabinet, calcium bicarbonate. That's more or less the same. It just has 2 carbons instead of 1. All right.
Father, talking also a quick component of what we'll get to eventually, I think, is a human impact on all this.
Yep.
And it's just a little short anecdote, personal story. We always used to go, because it came up now, to Marco Island when we were young.
Nice.
And you could actually find sand dollars. You go now, you won't find any sand dollars, primarily because people picked them up as tourist attractions for a while. But also there's been erosion and they filled in a lot of the beach from pumping out deeper. And I think they don't live that deep.
That's right, urbanization. So we can talk a little bit about the micro scale of things, of these sand dollars. Yeah, there is, even when they're live, you know, still grayish with all the little tiny spines on them. You throw them in chlorine water and they'll die, they'll lose all the spines, and then you get that white sand dollar that will last until you break it or someone sits on it. But yeah, souvenirs, but also the construction, the urbanization is occurring along the coast. Florida is probably #1 state for construction, especially along the coast, because that's high real estate money. And a lot of folks coming from the north and from the south migrated into Florida, and also from east and west. So we're getting a lot of migration into Florida, some of it with very little money and some of it with a lot of money. And so it's a nice retirement state, right? Because of its weather and so forth, except when we get the hurricanes. So a lot of urbanization is a challenge. That's really kind of the bottom line of this course at the very end, the challenge of the human. We have to live somewhere because we cannot live on thin air still. Well, the ISS, but the ISS holds very little people compared to 8 billion that we are. But how about the footprint, right? So we can try to make our footprint as eco-friendly as possible, because we got to live somewhere, but we got to leave enough space also for the rest of nature also to live. Yeah, challenging, very challenging. Okay, but not impossible. So there are solutions to this, and we just need to get creative and disciplined and enact the laws that will protect the environment. Anyway, this is the last thing I want to say before we take the break is the chemical composition of water, because pure water practically doesn't exist in nature, all right? Probably, what is the most pure water that you can think of in nature? Now that you know that water is the almost universal solvent, you leave water around, it's going to start getting solution of even microscopic particles that are floating around, and certainly salts dissolve in water, and they ionize, right? They dissociate, like what's sodium chloride? Sodium chloride, table salt, right? Table salt, you should never use it, throw it away. Don't use table salt, just get into the natural flavors and stuff, because table salt hardens your arteries, which increases blood pressure, and it doesn't happen now, it happens later, but it's higher risk of heart attack, okay? So don't use table salt, just get natural flavor. But basically, the ions dissociate, NaCl, right? So sodium, natrium is positive, and chlorine is negative. So when table salt goes into water, it ionizes, it dissociates, and you got the natrium floating around, and you got the chlorine floating around, and each one of those atoms will then be coated by molecules of water, okay? And that's the coating there that happens, so the solvency. Water has about a dozen minerals. I'm talking about ocean water. Ocean water has about a dozen minerals in it. That again, they ionize typically, and here's a little table of them. But water has an immense amount of material, of matter dissolved in it. Even gold is dissolved. I forget how many grams of gold in a ton of water. But there's even gold and silver and other metals dissolved in water floating around in the water column. So it's very difficult to find just pure clean water in nature, right? What's the cleanest water you're going to find generally?
Maybe rivers?
Well, you're thinking about liquid water, right? But
yes.
the springs, but even springs are mineral springs, right? So they have water, they have mineral. For example, the water here, the tap water that we drink has to be softened because it comes out as hard water and very alkaline. It's about 8.5 or 9 pH. 7 is neutral. And so it's softened down to about 8. Those are the water treatment plants that we have in town. It's clean water, clean in the sense that it's not contaminated with bacteria, but it's full of minerals. It's too rusty, it has too much iron, too much other minerals. And that's why the sprinklers from well water paint the wall orange, right? Because that's rust. The iron that comes out, we saw it in the SRI a few years ago in the summer, the water that comes out from the springs rusts, and then it turns reddish. So the cleanest water is not liquid water at all. It's water vapor. In other words, clouds are the cleanest water. And even clouds have a lot of contaminants in them. They have dust particles and other molecules that mix into the water vapor, all right? So there's practically no real pure H2O in nature. Precisely because water is a magnet that loves to attach to everything in sight. In fact, to cause rain, the water droplet, the water vapor needs to condense around a nucleus, around the seed. You've heard about seeding clouds, right? They throw iodine crystals or some other crystal out there to help as seed for the water vapor, the water molecules to start condensing. And when they condense enough to make a density react to gravity, then they're pulled down into toward the center of the earth. Of course, they never reach the center because they stay at the surface, and that's what makes rain. So it's practically impossible to find just pure H2O in nature. Okay. But with regards to the liquid water, because we're in the hydrosphere, whether it's lakes, rivers, or oceans, we can generally classify it into three general areas from least to most minerals or chemicals in the water. Fresh water will have the least amount, right? What is PPT? PPT, parts per 1,000, right? 1 order of magnitude less than million, or actually 3 orders, right? Because we got million, 100,000, tens of thousands, and then thousands. So, 3 orders of magnitude more than 1, 10, 100, 1,000, right? So parts per 1,000, fresh water in general, like springs and rivers, upriver, have less than 1 part per 1,000. Then the ocean is around 30, 32 to 37, about 35. If you have saltwater aquarium, you want to keep that PPT at about 35 parts per 1,000. There's a little hygrometer that you can float in the tank, in the aquarium, if you're keeping saltwater fish, right? To give you the salinity of the water, the density at about 35, because water is evaporating from the surface, right? But what evaporates from the surface? Pure water, H2O molecules, which means that over time, your aquarium at home, your saltwater aquarium is losing pure H2O molecules into the air conditioning system, into the atmosphere, into the air of the room, right? And so the volume will get lower and lower and lower on the aquarium, and which means that functionally what is happening, the salts are concentrating. They're concentrating inside the aquarium, and that's going to stress the fish, because now the fish are in saltier water than they're used to, okay? And it can actually kill the fish at some point. They get too stressed. So you want to maintain it at about 35 is the range for the average ocean water. In between is about, is what we call brackish water or estuaries. Estuaries is when rivers empty out into an ocean, not a lake, but an ocean, okay? And so it's going to be mixed between fresh water and salt water. It's called brackish water, brackish. And that's going to be halfway between 35 and 1, which is about 16, 15, 16, 17, right? It varies a lot according to what's flowing through there, if it's more fresh water that's flowing out or salt water that's flowing in, okay? And then in the oceans or seas, there's also quite a bit of range, right? The Black Sea, for example, is disappearing, is almost becoming a lake, the Black Sea, because the Black Sea is closed in, right? And is receiving a lot of rainwater and rivers that are running in, but is losing its salinity little by little. It's being, the outflow is the mineral composition of the Black Sea. So it's being little by little turned into a lake. It's got about half the salinity of the average ocean water. On the other hand, the Dead Sea It's about 10 times thicker, 10 times more dense than 10 times more dense than the average ocean water. And that's why it's called dead, because there's nothing living in there, where actually there is some living stuff, bacteria. These are bacteria that are called hydrophilic. They're extremophile bacteria. This particular bacteria, we saw it in the earlier course on fundamental principles, the beginning of life, phylogenetically. This bacteria are halophilic. Halo or halo is a reference to salt. They love salt, and that's the ones that grow there. And that's why the water is also very clear and crystalline, right? These are images of the Dead Sea, and you can float so high that you can actually read the newspaper on the Dead Sea, because your chest will not get wet. You float up high on the Dead Sea because it's very dense. It's actually viscous. It's like baby oil. You know, it's very viscous. But watch out, if you go, don't go in, don't put your face in, because if you put your face in, you'll feel, if you have a little cut, you'll feel it. It will sting like dipping in chili sauce. All right, and it will sting your eyes. So it's very dangerous to get your head inside. Don't put your head inside the Dead Sea, because it can cause damage. But you can float backwards, so you see floating. You also see on the Dead Sea, these little chunks, what you think is chunks of ice floating around, and it's not chunks of ice. It's actually chunks of salt that are floating around, because the Dead Sea is so dense in salt that it's actually condensing and forming chunks of salt, you know, crystals of salt. And it's a big mine industry, salt mine industry there, even from the Roman times, 2,000 years ago. One of the famous, the 7 roads of Rome, 7 roads that left the city of Rome in different directions in the Romans, ancient Roman 2,000 years ago, were famous for building the roads, right? In fact, a couple of centuries before the time of Christ, one of the roads went from Rome to the Middle East, to over here, where's my map? They went to the Middle East, from Rome here to Middle East is over here, Israel, okay? From here to here. It's called Via Salaria because it's a reference to salt. Yeah, but they didn't go around the land. They went by sea. So they went from Rome to Brindisi, Brindisium, this little further down here. And there you catch a boat and go to Greece, and then travel all the way down to the Athens area down here, and then across. That's not the cliffs of Dover there, okay? And then, so it was a land and marine route, right? A lot of commerce and navigation going around the Mediterranean back and forth. But to get salt precisely from the salt mines in the Dead Sea. In fact, the Dead Sea has now been split into 2. Here's the Dead Sea, okay? And the lower part of the Dead Sea is now disappearing. It's only about 4 or 5 feet deep. And you can see it's a huge, big salt mine. You can see how it's all already been fragmented, right? Artificially, those are not natural dikes that are being made to evaporate the sea a little faster and start mining or continue mining the salt from the Dead Sea. The Dead Sea is also one of the lowest points on Earth, about, I think it's maybe 100 feet or so below sea level. I don't know exactly how much, but it's below. And you have to be careful when you're down there, because not only is the water that is accumulated more dense because it evaporates and it has nowhere to go, right? But also the air is more thick, it's more dense because it's lower. And so there's proportionally more oxygen also. When we breathe the oxygen down there, there's proportionally more oxygen, and there's also more nitrogen. And there, the nitrogen does have an effect, is not as inert as at the surface of the ocean. What effect does nitrogen have down there? Breathing air, nitrogen, ambient nitrogen, it actually, because of the pressure, it actually does get into the body, and it causes something that is called nitrogen narcosis. nitrogen narcosis is equivalent to being drunk. So you have to be careful down there. You cannot breathe too fast because you start getting dizzy and lightheaded, and it's equivalent to being drunk. So you have to pace yourself and not breathe too heavily and not do too much exercise either, because with exercise we breathe more, right? That's the Dead Sea. It's a crevice of the earth. It's a fracture, natural fracture, as you can see it here, all the way down to Eliat, which is a town down here, which is a big tourist town, and it goes into the Indian Ocean. This is the Indian Ocean. It's a little sliver of the Indian Ocean. As you can see from here, the Arabic Sea, the peninsula, this is the Sinai Peninsula, and then the Arabic Peninsula, but this eventually empties out into the Indian Ocean or the Red Sea. Okay.
Father,
Yes.
speaking about the Dead Sea,
Yep.
and you were speaking earlier about erosion and kind of the flow of water and gravity and so on.
Yep.
I do believe that the tributary for the Dead Sea is the river Jordan that comes from Galilee.
Jordan,
The
yes.
Sea of Galilee.
Exactly.
So the Sea of Galilee is actually higher, right? And then it
Yes.
eroded down.
Yes, the Sea of Galilee, which is fed by some mountains that are around here, the mountain, that's precisely the heights of Lebanon. That's why that 6-day war, whatever it was, that the Israelis invaded over here and took over this area, the Golan Heights. The Golan Heights, there's Mount Hermon, right? Because all this mountain range is the one that feeds this rivers. You can see these ravines. These feed into the Sea of Galilee, which is also known as the Lake of Gennesaret of biblical fame. This is where Jesus began his public ministry up here, the Northern Kingdom, all right? And it's green and fertile because the Sea of Galilee is fresh water. And in fact, it was mixed water. There are also minerals coming down, but there are springs up here. And the Israelis already for quite a few decades ago have figured out which springs from Mount Hermon are more salty than others, and which are more fresh water and which are more salty water. And so they have isolated those, and they allow the fresh water to come into the Sea of Galilee, but the more salty water they channel, and there's a channel that goes all the way around. We may lose the scale, but it's near this road. There's a canal that channels the salty water out, so it doesn't go into the Sea of Galilee, and it goes all around the western shore of the Sea of Galilee by Capernaum, and then by Caesarea, not Caesarea, where was, where is that other city, Tiberias, which is also biblical and Roman. Anyway, that canal goes through here on the shore, near the shore, and it empties down into the Jordan. Here's the beginning of the Jordan River. Humble little beginning, all right, but very significant. That's the Jordan. And they empty that water here, and then the Jordan flows south into the Dead Sea. Here continues to Jordan, and it divides Jordan country with Israel, all right? It's the boundary. And that's why it's difficult to get down there, because it's off limits. That's the Jordan River there, meandering. So is it an ancient river? You better believe it, it's ancient, and it's carving away, right? And it should flow all the way down vertically into the Dead Sea. There's the Dead Sea. Okay. Right there, that's the flow, that's the delta there. And across from that are the famous Qumran, the caves of Qumran are around here somewhere, where they found the Dead Sea Scrolls, right, associated to the Dead Sea Scrolls. If because of the famous walls of Jericho, one of the oldest cities in the world. It has about 7 layers, going back to about 7,000 BC. All right. So a lot of history, ancient history, natural phenomena occurring. Here's the Sea of Galilee, freshwater. Here's the Dead Sea, salty, and the Jordan River in between. Okay. Israel on the left, Jordan on the right, etc., etc.
Sorry,
Okay.
Father, I have a
Mhm.
question. I'm sorry. So the Jordan River doesn't go through Jerusalem?
No, it's off to the side. Here's Jerusalem. It's up
Uh-huh.
higher. Yeah, it's
So
higher.
I'm sorry, but then the baptism, they needed to walk to the Jordan River?
Oh, yeah, right. Yeah. So, well, first of all, the city today is here, but then there was, you can call it a metropolitan Jerusalem area, okay, where there were outskirts of housing and so forth, buildings outside and settlements. But absolutely, the Jordan is way over here, so they had to walk here. And the rich had a donkey. And this is where generally John the Baptist was preaching conversion, baptizing with the baptism of repentance, not sacramental, and so on and so forth, right? And there's a little tiny reference that Jesus was also baptizing. It could be a corruption of the text. I'm not sure about that, but there's a little tiny reference there, at least in one of the Gospels, that Jordan was baptized and Jesus was also baptizing elsewhere, which is very intriguing to me from a theological perspective, because was that a sacramental baptism? Was that the institution of the sacramental baptism? Was he baptizing in the name of my dad, myself, and the Holy Spirit? I don't know. And it's intriguing, but there's a little passage where it says John was baptized in the baptism, and Jesus was also baptizing elsewhere in the Jordan. But it could also be a corruption of the text, which then brings other biblical and theological and scriptural issues into play.
Father, could I ask one more biblical question?
Why not? Go ahead.
So the water from the stones, how does that form?
Well, okay, it's a figure of speech, okay? We're not fundamentalists. And so, in fact, most of the Bible has not really been interpreted from the Catholic perspective, passages here and there, but it's a reference as it could be as water from the stones, okay? As if it were water from the stone. Oh, Father Daniel, very good. I'll show you this picture in a minute. Yes, as if it were water from the stones. In other words, the people of Israel were so hardened of heart to hear the message of the Messiah that Jesus would say it would be easier to bring out water from these stones, from the rocks in the middle of the desert. In other words, something that is practically impossible, than for some of these people to believe and to convert, because their heart had turned precisely into stone. So it's a play on words. The heart was harder than stone. It could be easier, more benevolent to get water out of these stones, these rocks in the middle of the desert, than for these people to have a heart of flesh, and convert and accept the gospel. Right? That's the reference there. And here, I don't know if you can see it on the camera, maybe. Can you see it on the camera?
Yes.
Yeah, okay,
Yes.
That's Father Dan. He's one of our, Daniel Good is one of our priests who's online, and he's baptizing someone at the Jordan there. Okay.
So
Father Dan, I hope you used the Trinitarian formula to make it sacramental. Yes.
I did. It was actually a very unique circumstance, because usually we wouldn't baptize an adult like that.
Right.
But it was a special circumstance. This young girl who was adopted, she wanted baptism really bad, and they were on this trip with me to the Holy Land. So we talked to their parish priest at home, and I agreed to baptize her, and then the parish would give her first communion and confirm her. So it really was awesome and special.
Absolutely, yes. So you were on pilgrimage, right? And it's called extraordinary circumstances. Normally, baptism for adults is done typically at the Easter Vigil with the other two sacraments of initiation, as you know, First Holy Communion and Confirmation. And Christina, the catechist, will keep us straight on this, right? But by exception, under special circumstances, it can be done the baptism first and then complete the sacraments of initiation when she returns to her parish, right? Fantastic, beautiful. Yeah.
Okay, and I'm sorry that I'm asking
Jump
more
right in.
questions about this, but since, oh, I'm sorry, my granddaughters are here, please excuse me.
Are they baptized?
Oh, yes, they're baptized. But my question is this, because I wasn't under the impression that the Jordan River, because of how the sacred scripture describes or narrates that John the Baptist was baptizing in the Jordan River, and it seems like the Jordan River was the place where people gather, right, on those days. Could it be, and this is just a question related to what we're learning today, that because of erosion and what we just discussed, the river has shrunk?
No, not
related
shrunk.
to-
Well, I mean, this would be, if you want to stretch out the Jordan River wide to reach Jerusalem, you would make it wider. You make it about 3 times wider than the Dead Sea, right? Which is not going to happen. This is a crevice of the earth. This is a low point of the earth. So the Jordan River is stuck down there, all right? It's carved its way through precisely the rock here to make this crevice, to make this canyon. But basically, no, people migrated. People went there also because it was a source of fresh water. So I'm sure there was a route going this way horizontally to the Jordan River. Maybe the Dead Sea was a little less salty, but not much less. In other words, this Dead Sea has been around for quite a few millennia already as extremely salty, okay? Rather, it was a place of pilgrimage, basically, and people were accustomed to making this passage. Well, I'm looking at a scale here, 5 miles, so probably it's about 10 to 15 miles from Jerusalem, which is essentially a day's walk, all right? A day's walk, 10 to 15 miles. And, but it was a source of fresh water. And also keep in mind the ritual ablutions that they would do. So it had everything pretty much in Jewish society had to do with religion, with faith and so forth. So everything was spiritualized. And they would do these ritual ablutions precisely because they lived in such a desertic area that having water was a sign of abundance, was a sign of blessing from the Lord, from Yahweh. And so they would cleanse themselves. In fact, that whole Qumran community, from which, as you may know, John is associated with the Qumran community, right? They were kind of monks of the time that lived in caves up here on the cliffs. And they had therefore different pools of water there where they would do the ritual ablution, sometimes 2 or 3 times a day. They would sink themselves and come out. And so it was like a pre-baptism. And it was a cleansing, ritualistic ritual that they had. All right. So they basically walked. And he preached here because here water was abundant. It was close to his home, the caves of Qumran, and in that community. It's not really known if Jesus was associated with the Qumran community or not. It's a lot of speculation about that. Okay. But basically, they did walk. Okay, Christina? Most of the people, most of the time, walk wherever they're going, even to this day, because most of the people today don't have transportation. If they can get on a public transport, they're lucky. I'm talking about worldwide. Okay.
If you think of the road in Jericho, that's quite a distance from
Yeah, Jericho.
to
Jericho.
Jerusalem, or from
Jerusalem.
Galilee to Nazareth, to Jerusalem.
Right. And so they talk about passing through Jericho or passing through Samaria, which would be here in the middle somewhere. Let's see, from the northern kingdom, which generally is green. I mean, you have to use a little imagination, but this is considered fertile. All right. Of course, it's not going to be as fertile as a fertile crescent. The delta. This is the delta of the Nile. Extremely fertile, right? Lots and lots of soil with lots and lots of water from the Nile River. But this, in comparison to this down here, this is considered fertile because there's a freshwater source. Mm-hmm. But yeah, that's the geography, Christina. We can't change it.
Thank you.
What it is.
I wish I can use this map in my classes next
Do
week.
it.
I'm gonna try. Thank you.
If you go, so if you have access online, all of you, we can all do this, you know, if you have access online, then just project it and just do a Google map. This is an actual map. These are photographs, satellite photographs that are put together, composite, you know, and you can go anywhere in the world, any place, anytime. Like for instance, right now into Miami, Broward, 95, there's a Golden Gate interchange, Bunch Park. I don't know why we appear as Bunch Park, but we are actually St. Thomas University is coming up. Here it is, there, we're zooming in, and we are right now in here. Okay, and that's as big as we can get. We are in here in this building. That's a photograph. That's a science building. And this is our beloved forest, the slash pine forest that we're trying to decontaminate from foreign species. And when you get real close, you see the pixelation. And you can actually look a little bit sideways, not much on the trees, also the canopies of the trees. But you can see a little bit sideways. See how the image moves a little bit? All right, see? This canopy over here of this tree is covering this ground area. Okay. That's the degree of resolution from satellite imaging. Scary. Other places of the world don't have this kind of resolution. You get a big blur, like if you try to look into Cuba or Iran or Russia, you get a big blur. Because this has military implications.
It is.
Okay, folks, we're going to go into currents after the break. It's already 11:25, so let's go to 11:35. Okay, 10 minutes, and we'll be back. So, pause recording. All right, welcome back, and here we go on the second half, which is going to be a shorter half of today's lecture on the hydrosphere. Gonna go back out to a big picture again, just rounding up the little discussion that we were having earlier. Notice how the influence of water on the world and on human population. See, even just Florida, most of the development is along the water, especially the southeast coast, right? But also on the west coast, we have Florida. And likewise, for many countries of the world, most of the populations or significant amount of population lives on the coasts. Okay, so back to water, back out to some of the currents of the ocean. Again, looking at these cycles, the dynamic cycles. Essentially, there are 5 main gyres or ocean currents that form and are circulating and maintain kind of a horizontal circulation on the surface of the ocean, so the surface of the earth. And it's, again, mostly by the Coriolis effect, right? Which is the rotation, the spinning of the earth on its axis. And of these 5, 2 are in the northern hemisphere and 3 are in the southern hemisphere. So we have the North Pacific gyre, the South Pacific gyre, the North Atlantic gyre, the South Atlantic gyre, and then the Indian Ocean gyre, which is in the southern hemisphere, right? And you notice that which, by the way, the pattern is opposite, the rotation is opposite to the atmospheric gyres or hurricanes, if you will. For example, you notice the North Atlantic gyre, yes, is rotating clockwise, right? It rotates clockwise, and it basically starts in the Gulf Stream. It starts in the Gulf of Mexico with shallow water that warms up, comes out through the Straits of Florida, right down here between Key West and Havana, and then it moves north as the Gulf Stream. We know it as the Gulf Stream. The Gulf Stream has been described as a river within the ocean, as a river of water, is warmer, saltier than the rest of the Atlantic Ocean, and it flows like a river. In fact, it has maybe 4 or 5 knots of speed. I think a knot is about 1.2 miles per hour, something like that. It's pretty fast flow of water. So much that if you're heading from the Bahamas to Florida to Miami, you have to account for the Gulf Stream, otherwise you run off course, right? So the Gulf Stream goes through, this is known as the Straits of Florida, between Cuba and Florida, goes through here and then heads north, bathing the Bahamas and going north pretty much vertically. And if you're going back and forth from Miami to Bahamas by boat, you have to account for the Gulf Stream. Otherwise, if you don't correct for that stream, for that flow of water, you miss the Bahamas if you're going that way, and you're going to miss Miami altogether. You end up in Palm Beach or even further north if you don't correct coming back. Anyway, the North Atlantic has its own gyre, which is clockwise, right? Opposite the gyres of it's very telling. Here seems to be like a hurricane or some kind of a formation that is counterclockwise. You can see it very graphically, the cloud formation. And that Gulf Stream goes across Cape Hatteras, which is the point, the easternmost point in the southern coast of the US, in the Carolinas, North Carolina, Cape Hatteras here, right? And then it zooms across the North Atlantic goes up into Ireland over here. And that's why Ireland is warmer than the British Isles and the rest by latitude, the rest of even continental Europe. And it seldom snows in Ireland. It's more warm or less cold and more wet because the Gulf Stream is taking warm air on top of it all the way out there. So the current, one thing is the ocean current, but then there are air currents that flow together with the ocean currents on top of it, right? So these gyres rotate in the northern hemisphere clockwise. In the southern hemisphere, they rotate counterclockwise, right? So you can see it here. So for example, this southern Atlantic gyre picks up water from Antarctica and goes up the western coast of Africa. As it does that, near the equator, it warms up and then heads down south along the coast of South America, making the coast of South America, the eastern coast of South America, warmer than by latitude, right? It should be temperate, and it's actually kind of tropical, subtropical, because of the warm waters flowing down. And as that, it's called the Brazil current for obvious reasons, sinks down into Antarctica, then it cools again and starts the same circular motion back up around, okay? The Indian Ocean, the same motion is counterclockwise, and the Pacific gyre, the South Pacific gyre, is huge compared to the other two, and the North Pacific gyre is also huge compared to the other two. So the North Pacific gyre in particular, because it covers a lot of the landmass, so most of the landmass again is in the northern hemisphere, and there's a lot of population along North America, the whole coast of all the way from Alaska through Canada, down the US, Mexico, and Central America, a lot of population there, right? Human population, plus the mountain ranges, the rivers that flow toward the Pacific. They carry a lot of stuff with them. And then in Asia also, there is so much population along the coast here, you got the Philippines, you got Japan, you got Koreas, and even parts of China, the North China Sea and all that. So this is high density of human population. Plastics, a lot of plastics are ending up in the North Pacific. Now, all 5 gyres have what is known as a garbage patch on them, have a garbage patch. But the one that is the biggest is in the North Pacific, all right? So it's known as the Great Pacific Garbage Patch. The Great Pacific Garbage Patch is a 4-minute video that we can see. But whoa. I want to go into the mode of optimizing video clip. And then maximize the window. Okay, so stuff that is floating.
Earth, the globe, Terra, our world.
Sound, more sound down here. Okay. Maybe too loud, but I can bring it down. Okay, let's try that. All right.
No matter what you call planet Earth, it is our home. In the small span of time the Homo sapien has existed, we have made profound impacts on the condition of our planet. From the depths of the jungle to the heights of the mountaintops, the human footprint is encountered across the expanse of the globe. One of the most prolific impacts humanity has had on our world lies in our oceans. Human waste, specifically plastics, have built up in our oceans, posing an imminent threat not only to nature, but to humans as well. The Great Pacific Garbage Patch illustrates the effects that we as humans have had on the marine environment. Located in the northern Pacific Ocean and the largest of 5 garbage patches, the Great Pacific Garbage Patch is the product of tons of debris which have made their way into the ocean from lakes, rivers, and streams. The garbage caught in this patch is unable to escape, caught in a vortex created by ocean currents. The patch, more than 3 times the size of Texas, spans from the coast of Japan all the way to Hawaii and even to California. Furthermore, the total amount of garbage in the patch is impossible to calculate because of the thick layers of built-up waste.
The scuba diver, he's right under the surface and he has a camera. And this pole that's sticking out, he's got a camera there. So he's doing a selfie basically, right? He's doing a selfie. And what you see on top, he's just below the surface.
A lot of the garbage in the water is made up of type N plastics, consisting of abandoned fishing nets and plastic rope. Type H hard plastics and type F foam plastics also comprise large portions of the patch. Since more than 180 times more plastic than food is found at the surface of the garbage patch, unsuspecting sea life, such as sea turtles, can have up to 74% of their diets composed of this ocean plastic. Although it may appear that the effects of the garbage patch end with marine life, it has become evident that these patches lead to detrimental effects for human life as well. While plastic does not organically degrade, it does still break down into what experts have termed microplastics. These tiny fragments of plastic.
We'll be talking more about microplastics later in the course, all right? But this is one major concern.
Enter our food supply through seafood and sea salt. Once in our digestive systems, they disrupt the human endocrine system and throw our hormones out of balance. The effects of the Great Pacific Garbage Patch are extensive. However, humans can help orchestrate a change. First, we must acknowledge that our actions do have an impact on the environment, whether we think they do or not. As an individual, a family member, and a community, you possess the power to effect a change. Organizations such as 4Ocean and the Ocean Cleanup fund and conduct research towards this cause. By donating and volunteering, you can help make a difference. However, supporting such organizations is not the only way to help. You can make an impact as an individual through recycling plastic bottles and containers, reducing the amount of plastic you use, and reusing your current plastic products. Spread awareness.
So those are the 3 R's, okay? Reduce, reuse, and recycle. We'll get into them.
On the effect of waste and microplastics in our oceans by being an advocate for our oceans, our sea life, and our species. Change starts with you. We created this problem, so together we can solve it to create a future for our world, planet, and home.
Those are 2 big companies now that are trying to make it sustainable and to recycle plastic and garbage in general, non-breakable, non-organic garbage. 4Oceans is one, and then the Ocean Cleanup. They're worldwide and they're getting a lot of traction. Very creative. I'll show you more interesting equipment, machines that they have made to collect garbage and to recycle it. So just a little foretaste, but basically these gyres are now concentrating garbage as they rotate, and especially the plastics that float around or are in the water column, and they will take centuries, maybe millennia, we don't know really how long, to decompose and break down. But even if they do break down, the microfibers and the microplastics are still a problem because they get into the food web, all right? And eventually we end up eating the fish or the scallops, the clams, whatever. So that's a challenge. Okay, I want to take a little different direction now and just clarify the difference between the 2 poles. It's a little too big. Right? So we have the North Pole and the South Pole, the Arctic and the Antarctic. For example, here is the Arctic Circle, which covers also a big part of Siberia and Scandinavia, Northern Europe. Then most of Greenland, which is this island here, right? Huge island. And then the northern part is essentially Canada and a little bit of Alaska is the Arctic Circle. Whereas Antarctica is a continent by itself. It's an actual continent, all right? But this patch of ice that we call the North Pole, it is definitely ice, but it wasn't known. There was a suspicion there was no continent underneath, but it wasn't really known. And it wasn't until the Nautilus submarine that it was finally established for good that the North Pole, in contrast with the South Pole, is not a continent. There's no landmass underneath. It's just a huge cube of ice. It's a huge chunk of ice up here. And why the submarine has to do with this? Finding this out empirically, definitely determining that there's no continent underneath. If it's an ice cube, right? If it's a chunk of ice that's floating on the top of the surface of the North Atlantic, what's underneath? Yeah, liquid water, liquid water. And so in principle, someone could go through it without crashing into a continent, right? But there were no submarines. There were submarines before, but there were diesel submarines. And no submarine had enough fuel to go underneath for whatever days it takes, I don't know how long, to go underneath the ice cap from one end to the other, until the first nuclear sub. And the Nautilus was the first nuclear sub back in 1958. And so it was the one that did the crossing from the North Atlantic to the North Pacific, or vice versa, I forget which way, but basically all the way through underneath. And in some points, my brother told me actually that the, I don't know what they call the sails. I think they're called the sails. all the antenna that stick out on top of the submarine. So the bottom of the submarine was almost scratching the surface of the bottom of the ocean, and the sails were scratching the ice cap, the bottom of the ice. It was very narrow. It was just a few dozen feet. So this ice cube almost goes to the bottom of the Atlantic, but not quite. There's water, there's liquid water underneath. Yeah. Anyway, okay, so just a point of interest that in contrast to the South Pole, which is an actual continent, one of the largest continents, the North Pole is liquid water underneath, okay? Which means that this ice cap is also dynamic. It expands and shrinks during different seasons of weather, the weather seasons, but slowly but surely it's getting smaller and smaller. So basically that ice cube up there is melting down slowly but surely, all right? And it's holding, I mean, the two most significant amounts of solid water on Earth are what? The two most significant solid water on Earth. The two poles.
Yeah.
Yeah, the North Pole and the South Pole, right? And so when the North Pole the South Pole can melt for sure into the ocean, but when the North Pole melts, that cube is gone, the water level will be significantly higher, okay? So keep that in mind. I'll show you a time-lapse photography over decades on how the North Pole is shrinking. It expands and contracts, but every time it contracts a little bit more, and it expands a little bit less. So the net effect is a shrinking. More to come. All right. Another important bit of information. Basically, as you can see here, we're establishing the natural phenomena, becoming more familiar with natural phenomena in some level of detail, so that we can talk intelligently about climate change and global warming. Is it happening? Is it not happening? And what is the human contribution to it? All right, because these are cycles. And that's the point of this graph, that there are natural cycles of thawing and freezing of the Earth the past 500 years, 500,000 years, in the past 500,000 years. We have evidence of at least 4 major glacier and interglacial periods. So again, this little graph down here. $400,000, so this would be 450,000, so less than 500,000 years, and the Earth has 4.5 billion years, right? So billion is 10 to the 9, is 4,500 million years, okay, in less than 1 million years. We have had 4 ice ages. Well, the interglacial, glacial, interglacial. The peak is above 30 degrees, between 30 and 40 degrees is what we call a tropicalization of the Earth, right? Where the poles essentially melt. And then the temperature goes down to 20. This is in Fahrenheit, meaning that at 20 it has frozen, because at 32 it freezes. I put a line here at 30. This is the freezing, thawing line, 30 degrees Fahrenheit, the scale is in Fahrenheit. So this is a glacial period down here. This is a winterization, then tropicalization, interglacial, down. There was a mini ice age here. Then a longer, a mini thaw, but a longer glacial period, right? Between 350 and 150,000 years. This big one here, and then another tropicalization, and the most recent one to about 10,000 years ago. 10 to 12,000 years ago was the last glacial period. Over here, we bring this down. That's 50. So if we put ticks of 5 ticks here, this one was 10 to 12,000 years ago, was the last melting of the last glacial period. All right. Our forests, for example, they'd start back to back then. because that's when these pines, which are conifers from up north, adapted to a subtropical environment. Not the individual trees that are there, because those trees, the lifespan is 150 to 200 years, but the forest as a whole, the whole peninsula of Florida was essentially covered with slash pine up to about 10 to 12,000 years ago. All right, so you see, here's an example, very graphic. Here's a glacial river coming down to, again, I think these are called cirques, where the glacier starts melting. And here's an interglacial period, right, where the glacier has been melted away. There's some little bit of ice left up here, but all this ravine down here is now melted away. These are actual photos, so it's been in the past few decades that cameras were around. I don't know where this is, probably the Alps, or it could be the Himalayas, but it's some kind of large bunch of range. As you can see, there's still permanent snow there, but this glacier is gone. All right, so when we talk about climate change, this is definitely climate change. Over thousands and thousands of years, the back and forth between tropicalization and winterization of the earth, okay? And the last one, 10,000 years ago, we were barely around, just chasing animals in the wild with a spear and arrows, all right? So there was definitely no industrialization, no significant industrial CO2 being produced. So these glacial and interglacial periods, we had nothing to do with them, and this was pretty drastic climate change, okay? So climate change has been around over long periods of time, but now the big question is, what is the anthropogenic factor? What is the human contribution to the current climate change, if there is such a thing? Okay, one last thing with regards to the natural world of water and how it's distributed. To get in here and lower the scale. Yes. So the amount of fresh water that is available naturally is very, very tiny from all the water in the world, all right? If we take all the water in the world, the vast majority of it is oceans, 97%. So 97% is salt water, which is not available for drinking, and very hard to even shower with it because the soap doesn't make a lather, et cetera, et cetera. So basically 97% of the natural water on Earth is unavailable for humans to use. Of that 3% fresh water, the vast majority of that is taken up in glaciers and the ice caps, mostly the ice caps. Yeah. So almost 80%, 79% is the North Pole and the South Pole. And then Greenland, which has a huge glacier on top of it, and a few glaciers that are remaining in the Andes, in the Himalayas and the Alps and the Rockies. So of the 20%, let me see. Yeah, so almost 80% is unavailable. It's solid water, right? In glaciers and ice caps. Then 20% remaining is groundwater, meaning under the earth, right? Not flowing above, no lakes, no rivers, but it's groundwater. So surface water is only about 1% of a 3%. 1% of a 3%. Then of that 1% that's available, almost half of that is lakes. The other half is divided into moisture, which is taken up in the soil, unavailable for drinking, right? It's mostly for plant drinking. The plants take up this moisture. Then water vapor, which again is unavailable for human consumption. 1% of that is rivers. And finally, 1% of 1% of 3% is available for humans. So very, very tiny fraction of the water on Earth is actually being used for humans, for the 8 billion that we are, to keep us alive. Very, very tiny fraction. So you can see what's the most obvious first water to tap into, the easiest water to tap into for us to use in large quantity. The lakes, yeah, rivers, but especially lakes, right? Because that's half of this 1% of 3%. And generally they're freshwater with more, some salinity, but generally. So the lakes are the first one. And in fact, you see today quite a number of, for centuries, millennia, people have been establishing around lakes for source of fresh water, all right? But eventually, if we go up, well, groundwater also, basically, we use groundwater. We use the Florida aquifer, the water table underneath the soil. All right, we have to break through the limestone and all that. But you make a hole in Miami 4 or 5 feet deep, and you start getting the aquifer coming up. You start getting groundwater. Eventually, it will be the oceans, but the problem is desalinization, which today is still fairly expensive. You have to go through membranes and things like that to filter out the salt. And it can be done, especially because salt is ionized, right? Cations and anions. So with electricity, with electrodes, you can capture the minerals out of salt water and make it fresh. But it's high energy needed to do that electricity, the electrolysis, and it's expensive. But there are desalinization plants. For example, I think most of the water in Key West from a desalinization plant that is at the base, at the naval base that they use, and that pumps, it's for the base, and they have excess, and I think they pump at least some of that into Key West, because Key West has a problem with fresh water. Okay, so this has been mostly natural hydrosphere, following the cycle of water in nature, from all the way from the molecular level up to the oceans, which are the largest bodies of water on Earth. Okay, different dynamics there. And now just a few words on the more the theological side, philosophical and theological. All of the recent posts have spoken about water, but with an increasing interest and urgency about water and the access for water. We can say that anything that is necessary for keeping us alive, we have a natural right to, right? So we have a natural right to air, to breathe, which so far is still fairly okay. And of course, in high population areas, there's smog and all that. And people do wear masks, not for COVID, but for purifying the air a little bit, for filtering the air. But water is a different story. Water is more difficult, especially clean liquid water for drinking and for washing. All right. So there have been an increasing number of conferences and documents from the Vatican appealing for the countries of the world to make water accessible for the people, because to this day, that, I mean, sometimes we associate this with ancient times, right? People going to the river with pottery to collect water and bring it. And but to this day, many children spend their lifetime, their childhood, going to the river or to the lake to get water to bring home, and then boil that water so they can drink it and they can wash with it and so forth. You know, and many of them don't even have a chance to go to school because they have to go get water. And water is heavy, so they have to be going back and forth. And this is on a daily basis in many countries of the world, in more developing countries and so forth. So Pope Francis, in particular, you know, he has a big interest for the environment and ecological awareness. So he had a conference on water precisely the year when I started, the year after I started the program. I started in 2016. And in February of 2017, so we were still, the first cohort was still moving through. They were in the second half of the program. This conference occurred in the Vatican. It was an international conference of access to water. Many delegates came from all over the world, and the Pope gave a speech. So I sent you a little copy. I think I included it, several texts of various popes talking about the right to water and how we need to work on that. Providentially, just recently, because this issue is not going away, just recently the Vatican published another document. This would be like the most recent document. It's called Aqua Fons Vitae. Which is in Latin, because Latin is still the official language of the Catholic Church. And this is the document. I'm going to send you a link to it. All right. So you can take a look. You can read it in English or French or Espanol or Italian if you want. But basically, this is the latest document that has come out. It came out in, I think, in 2020. Yeah, March of 2020. And water, the fountain of life or the source of life, right? And it covers many, many different aspects about water. Not only the dire need for having clean water available to the populations of the world, it also talks about the symbol of water, how we use it, for example, in baptism and in other sacraments. So it's really not just physical life, it's also spiritual life. It talks about the beauty of water, the aesthetics, and so many things about it. It's a very complete document, right? Kind of bringing in many different sources into a complete document, but basically the bottom line appeal is for everyone to mobilize to try to have clean water available for the peoples of the world, especially many people who today still don't have water. This comes out from the dicastery of promoting human integral development. And these dicasteries are, this is their website, their homepage. Dicasteries in the Vatican are like offices or departments or ministries, right, for other organizations. It's just an office, it's an old name for a department of the Vatican that looks at particular issues. And this one is focused on, like the word says, integral human development, all right? It's one that was generated by Pope Francis to integrate several other dicasteries that were around. This one in particular focuses on human, not only human survival, but human thriving, because we have a right to thrive in humanity, not just barely survive, all right, at the survival level. I know some people here, in fact, they came to give us a conference one in 2015, was the encyclical of Pope Francis that we'll talk about some more. Laudato Si, on care for our common home, the first encyclical in the history of the Catholic Church dedicated to the environment. That was Laudato Si. And it came out from, well, it was an encyclical in the Catholic Church is the highest level of authority. And it's written, well, it's written by the Pope, but in consultation with many, many other experts. Okay, this is it, care for our common home. This one was published in 2015. It was the first encyclical in the history of the Catholic Church devoted to the environment and, of course, to the poor, which are the greatest impacted by the degradation of the environment. This one came out in 2015, and it's one of the motivators that I have for launching, for putting together this program on bioethics, including the environmental bioethics. Okay. So anyway, Pope Francis is raising a lot of awareness. He gives talks at the UNs, at United Nations, and other parts of the world to try to get people to think about water, being conscious. So plastics are a problem. These little things are a problem. Single-use plastic is a big problem, you know, because this, once I drink this and I throw it out, this will last in the environment. Who knows how many centuries or millennia? Okay, and it's just an increasing amount.
Father Chelsea.
Yet it's the easiest way to move water around and to sell water and to buy water that is clean, right? You hope that the inside is clean. So it's a big, big problem. It's useful, practical, but how do we reduce plastic or make it biodegradable? I don't know. They get very creative. Cristina.
Yes, so I understand. I understand the issue of water, but there is I just wanted to clarify it in my mind. It is related to, of course, it's only 1% of the 1% that is available for human life. I get that.
1% of 1% of 3%.
1%. Okay, so that I understand, which is, it's something that shocks me in a little bit because the issue seems to be huge. And people say that maybe the third world could be related to water. But at the end, the amount of water that we need is not that large in relationship to what we have available on Earth. So, but my point is, or my question is it because of the contamination of water that it has decreased the possibility of water in the world for people to have it? Or is it because there are parts of the continents that don't have enough sources of water? Because those two things could be, like if you go to Europe, people cannot take showers every day, like what we do here, or things like that. And just in my mind, I wanted to make another comment, and that is, I work for St. Hugh, and in the year 2015, I believe, or we have a bishop that came, through the office of, anyway, to make a long story short, we, through the donation of people of St. Hugh, we had been able to build more than 36 water
tanks, containers.
No,
Wells.
Yes, wells. And it's been incredible. We have been able to provide the possibility because, yes, even this bishop that I admire so much, the water that is in the river that they have to walk 4 or 5 hours to get is so contaminated that they cannot drink it. And even if they boil it, it's not enough. So
Right.
what the holes that they got to dig and to find out, find the water that is fresh is so profound that it costs a lot. That's really the cost, making the hole so that they can get to the source of fresh
Right.
water. Anyway, those are just a question. Thank you, Father.
Right. So yours is a very complex question, and precisely those are the challenges, right? So it takes many minds to be able to solve these questions. They are challenging. Now, in principle, we need to say that it's not impossible because life is not impossible. We may make it impossible, right? But God created us to live possibly on Earth and to live correctly. But you can see that a lot of it is some are natural factors, like, for example, naturally contaminated water is not clean. You have to dig very deeply to get clean water and so forth. That's natural. But then there's a human factor. The human factor, one way or another, is going to boil down to corruption, right? Why do we have clean water? Why? When I get up in the morning, I go to the bathroom, I open the water in my sink, I get clean water. I get tap water running out clean. I've been drinking tap water in Miami for 52 years, and I'm not dead. So obviously the water has not killed me, and so we have clean tap water in Miami. Now go to Haiti and try to get clean water from the tap, or go to anywhere else, Mexico, and try to get clean water from the tap. And it's impossible. And so why? Why do we have it and they don't have it? At the end of the whole thing, when we do the analysis, it's corruption, because here the system kind of works. Down there, the system doesn't work because there's corruption all over the place. So there's a very much human factor. There's a human factor, right? We're supposed to be recycling. We're supposed to separate the plastic, the organics from the non-organics. But then when I'm getting kind of ahead of myself here, but when the water management, the waste management, or whatever garbage collecting thing comes around, then back in the factory, they put it all together and then they burn it. They get electricity out of that, but they're producing CO2. So there's no recycling going on in the Miami-Dade County right now. It's a big scandal. They ship it to Broward, and in Broward, they incinerate it. See? So there's corruption all over the place. We have some of the least corruption, we think, in the world. In other places, it's much more drastic. It's systematic, but it comes down to the human factor. There's no substitute for conscience. And there's no substitute for a well-formed conscience. And that's why we're all here, to educate ourselves with a well-formed conscience and make a difference. Like the Pope says, mobilize and make a difference. Get other people to be conscious about water, and don't do single use, reuse at least reuse the plastic until it breaks down or something. But it's a big problem. And you say, yes, it could be that the next war will be about water. There's already war between countries about water, about liquid water, because one country has water and the other country doesn't have water. Or sometimes they're stealing water from each other. States sometimes steal water from each other, or they dam the river, upriver, and then downriver, and the next state, they don't get the water because it's being dammed upriver. So that's a problem. Some states are selling water and buying water for their population. So it's we got to work it out. And the beginning of working it out is at least to have information, to have the knowledge, right? And then we can go from there. But it's a work in progress, and I understand the frustration. And so we do these wells in other countries, called third world countries or developing countries or poor countries. And it helps a little, but it's kind of a drop in the bucket, pardon the pun, but it's a drop in the bucket. We have to get a more systematic, deeper, which is the issue of corruption. No question, that's the issue of corruption. So that's why you're teaching catechism.
Thank you.
Yeah, and that's why the Vatican and the Pope keep speaking out. And he's not popular when he talks about environment to some people, but he's saying the truth. We have to assume the responsibility of contaminating the world. Animals are not producing plastic. Plants don't produce plastic. We produce plastic. So how to shift the economy so that it's still a sustainable economy, but not based on waste. The market economy right now basically is waste. It's consumer and obsolete and consume. And in the meantime, there's all this waste. One thing that frustrates me in the next couple of minutes that I have is anytime I buy something, I have to go through a package. And now it's not just one package, it's now 2 packages. It's horrible. You buy something and you have to crack it open, typically some kind of plastic, and then you have a second. It's like, we want this thing to be super sterilized. What's wrong? Why can't they say just if you buy, I don't know, a pair of pliers, that has to be packaged. Why can't you just buy the pair of pliers without having to be packaged in plastic? It's just incredible. Everything is packaged. Food is packaged, everything. So it's a big challenge. These are the things that we need to get creative. Like I'll show you a little later on when we look about energetics. A lot of it has to do with producing energy in a sustainable and a clean way, and how some people and companies and countries are becoming more smart about generating clean energy for industry. Because at the end of the day, one of the ones that uses most fossil fuels is going to be industry, because it's the cheapest fuel around. It's still the cheapest. So they have to meet the costs, right, for their investors. Okay, any other comment? Yeah.
Yeah, just this is more of a comment.
Okay.
So even let me put it this way: even within people that have, I would say, a similar conscious theological background, there's not unity on, like you say, the components of the environment. So I attended the conference that was at St. Thomas many years ago in Laudato.
Yes.
The
international conference.
Right. That was amazing. Very great learning. But at the same time, especially during that period of time, there was a lot of pushback.
Yes.
On the subject, and there still is, and there's a polarization. So that's where my component is. How do you go filter that? Because I can talk to some folks that have a very greater theological formation than I do, and they're very much towards still kind of that industrial individualism mindset. That there shouldn't be any regulation, there shouldn't be any structure. We should be free, and we should be. But again, how do you speak to that? It might be somewhat complex, but how do you speak to that in front that kind of counter argument as
Yeah.
opposed to embracing our neighbor, which is really, our second greatest commandment, right? We love our God, we love our neighbor, and this is what I
Absolutely.
think it's about.
Absolutely. It has to be, of course, a responsible, mature love, which is going to be challenged, right? Because it's going to be sacrificial. But yes, so that's kind of the big question for this particular course, and how to address the issues of climate change and so forth rationally, that we have an intelligible argument to present. And also, it's not going to be one single solution either. So the fact that there's not unity may actually be to the good, in the sense that when there's competition, there's challenge, and then creativity comes forward, right? Because when there's no challenge or competition, we kind of coast and stay with the program and don't do any innovation. But in this area, we need a lot of innovation. We need industry to continue to be sustainable, to be productive, and at the same time, the products need to be more eco-friendly. So it's a challenge. I like Augustine's, the little saying attributed to St. Augustine, in non-essentials, diversity, in essentials, unity, and in all things, Christ. So I think that there may be a silver lining in not being united in all this, in that it challenges, for example, the eco-friendlies, if you will, the ones who have an eco-conscience, challenges us to come up with the best arguments, even technologically, to move those who are doing the pushback, like you say, typically because, well, on the one hand, they want the freedom and this saying of a liberal economy, right? Which is the least government is the best government. It's kind of a phrase that is used for market economy, for liberal economic thinking. And at the same time, that is also sustainable, because if we leave it totally to the conscious individual, it's not going to happen. That's precisely what we have now in countries where the individuals in power don't have a well-formed conscience, and therefore they're exploiting the people, they're exploiting the resources and the natural resources and so forth. So it's a complex thing, and one size doesn't fit all. We actually need many different sizes of colors, shoes, and models, and all this. Okay, but the cluster of things should work between hydroelectric and wind electric and solar and so forth, even nuclear, alternative energy sources. These things, they have to make economic sense also. All right. But there's a shift. I think that gradually the younger generation is definitely more eco-friendly, right? Now, what we need with the younger generation is also to be human life friendly, consistent from conception to natural death. So these issues go back and forth. But anyway, that's a good prop for kind of ending here, because the rest of the course is going to be looking, we still need to look at a few more things. We need to look at natural cycles on Earth. And then we'll look at energy sources. And after those two lectures, we're going to dive more deeply into the issues about climate change, the evidence for that, and what would be some possible solutions. So we're getting there. Hang in there. Just keep accumulating data and thinking about it. Read these documents. So I'm going to send you this afternoon, when I send you the link to the video, I'll send you the link to the document also, the water document from the Vatican. Not this one, but this one.
Fue agua fuente de vida.
Sí, agua fuente de vida. So take a little time to read it, and it should be uplifting. Okay.
Actually, Laudato Si is so powerful.
Yeah.
I really recommend everybody to read it, because
Yeah.
it is
Laudato Si.
fascinating. And
Yeah.
like theology of the environment, is how they call it, theology of the environment.
Yeah.
I love it. It's beautiful, but this is going to be great to read. Thank you.
Okay. Very good. Excellent. Anything else? You go good? All right. Thank you very much. God willing. So let me see. Next Saturday is still September, right? So next Saturday we still have lecture. Then the first Saturday of October, I have Prison Ministries, so there will be no lecture for then. All right. But next
Father,
Saturday, we still have.
next Saturday is October the 1st.
Next Saturday is October
Is
1st.
that it? Oh, yes, you're right. Thank you very much. Thank you. Okay, so next Saturday, no lecture next Saturday. All right. No lecture, no summary, but the summary from today is still due this weekend. It's still due this Wednesday. If you want more time, for this summary, since there are gonna be 2 weeks. If you want, okay, so if you want time until Friday, so that I can correct it at some point, right? If you want time until Friday for this weekend instead of Wednesday, that's fine. Mhm. Yes, Kenny?
I was gonna say, yeah.
Yeah.
I think it'd be best
That
if
helps?
Friday.
Yeah.
Well, with the hurricane coming.
Oh, yes, that's right. Wow. Yes. Okay. Thanks for that. Yes, good. Okay. So we have a reason. All right. So let's make it for Friday instead of Wednesday. And by Friday, we should know if we're still in the corner projection or not. Okay. Thanks again. So we'll see you in 2 Saturdays.
Thank you, Father. It was fantastic. Thank you.
Okay. Thanks again.
Thank you.
Bye all.
Bye. Okay.
Bye-bye.
Alicia. Okay, and Ken and Sarah, and then stop share and